Okay, good morning, everybody. I hope everyone's having a wonderful day. So today I'm going to be talking about something a little different than we have in the last little while, but this should fit into everything we've been discussing up to this point. I want to talk about so-called lower bounds, and we're going to use the examples of searching and sorting to discuss this. So just to kind of back up one moment, very often up to this point in your studies, you have addressed and come across questions kind of like this, that there is a big O time algorithm for blank, or big theta in this case, I have written here, a big theta of some function time algorithm for blank, where blank is some problem. So we've been doing and considering things like this. For example, we talked about linear search earlier. We said, okay, well, that means that there's a big theta of n time algorithm for the search problem, for example. If I'm given an array of length n, I want to know whether the element is there or not. So in those cases, we have algorithms that solve them, and we have some efficiency that we care about, right? So just to give you an idea of what I mean, I'm going to say often you will be told that, or of course, or learn algorithms that are claimed to be best possible. I'll say best known. I think best known is a bit more neutral. Best known, or sometimes in some cases it might even be optimal, as in like it's the best possible in terms of its efficiency, in terms of complexity. So in case, for example, we're talking about time complexity. So very often we run into cases like this. So oftentimes people would like to have some way of talking about the best known algorithms for a given problem. And oftentimes when we talk about a problem, we might refer to so-called upper bounds for solving a problem. So this would be the complexity, usually worst case when it's not quantified, but complexity of the best known algorithm that solves it. So whenever somebody tells you, oh, okay, we're talking about the best known algorithm to solve a problem, there's many examples I could point to of problems that you're familiar with. So for example, we talked about the search problem. So imagine I give you the search problem, and say I give you an array L, and its length is n. So just as an example, a best known algorithm for searching in an array of length n, given some array L, an upper bound for this problem, for example, is big theta of n. And you know an algorithm that actually achieves this. Can somebody tell me in the chat, or tell me what's an algorithm you know that solves this problem in linear time? The linear search. That's a good answer. I like that one. So you know one like that. It's linear search. So oftentimes when we're studying problems, we're caring about the complexity of solving them, and we have this best known kind of bounds that we have, and there may be several of them. Sometimes it's because there's trade-offs that occur between certain parameters that a problem has, which does occur sometimes. But oftentimes for these more classic problems, there's just one, bam, there it is. It comes at you, bam, there it is. So this is one, for example. This upper bound, I'm getting ahead of myself. This upper bound is true for unsorted arrays. So if I know the array is completely I don't know anything about the array, This is the best known algorithm. This is one of them for this problem. And in fact, I'll get a little ahead of myself. If you're wondering what lower bound means, that is literally the minimum amount of time necessary to solve the problem. Or in our case, minimum amount of complexity you need to solve the problem. And if I told you, just give you a heads up, if I told you it's linear time, that means that if you think about linear search, you can think of it as an optimal algorithm. So that's why I mean the word by optimal, is that if the upper bounds on a problem and the lower bounds of a problem meet, meaning that our lower bound results are good enough to capture the upper bound case, that means that we could say that you can't do any better than that. And in fact, we have algorithms that do it. And oftentimes people will tell you, okay, that means that you've solved the problem. And then there's more narrow things we can talk about. But I'm going to get into more detail about that in a moment. So if you're wondering about what the heck I just said, I will get into more detail in a bit. Okay, now I want to talk about sorting. So in this case, I am going to go into a little bit of detail, but I am not going to assume much background with sorting. But in 210, you will have seen all the algorithms I'm going to talk about, but not necessarily in the depth I'm going to touch them. So some of these we're going to touch on later on the course. Others, I'm just going to kind of remind you of them, and then I'm just going to plow right ahead. So some of these results you're going to be familiar with. So first, for sorting, you may know some algorithms that are actually, they match so-called the best known ones for general sorting. So a good example one is merge sort. Merge sort, this has worst case time complexity of big theta n log n. So that's one. Can somebody tell me another algorithm that has worst case time complexity of n log n for sorting generally? It starts with what I'm looking for starts with an H. Starts with an H. Heap sort. Yeah, perfect. That's the one I was thinking of. So heap sort is another one. We'll definitely touch upon heap sort later. We'll talk about both of these at some point in this course again. So heap sort, perfect. People are getting on heap sort. I want to make a remark about one other sorting algorithm you may have learned. It's the one king or queen, however you want to phrase it. It's quicksort. I want to touch on quicksort for a couple of good reasons, because asymptotically speaking, there are many variants of quicksort, depending on what you do with quicksort. So you may have heard of so-called pivoting strategies. I want to touch upon this just a little bit so that you're aware of some background. And it's okay if you've never... Oh, the video did... Yeah, let me fix that quickly. My apologies. That's pretty funny looking. Let me fix that. Let me deactivate. Activate. There we go. Perfect. There. I think we're good now. Okay. There we go. No, don't worry. It's okay. Your internet's doing okay. It was okay. That was a fun glitch. It seems like this week is a very glitchy week. First Windows and now my rendering stuff. I think we're good now. Does everybody see me perfectly fine? Just want to make sure. That was kind of funny looking. That's what it looks like after a long week. Okay. So, yeah, I see thumbs up, so let me proceed. So I'm going to talk briefly about quicksort. First, I'm just going to remind you roughly, just going to draw a couple pictures just to remind you of what quicksort does. I'm not going to go into the details of quicksort because you've probably seen a bit about quicksort before. So the first thing I can say is that in quicksort, the biggest and most important thing when we think about quicksort is the so-called pivoting strategy that you use with quicksort. I'm just going to first write down kind of the worst possible scenario when it comes to quicksort. This is the one you may have learned, is that it takes big O of n squared in the worst case. And I must remark, you may or may not have seen this, but I want to remark, and this is something I want you to just be aware of, is that in the average case, it actually is big O of n log n. So that matches those guys over there, but that's in the average case. So this should naturally reflect for you the practicality of quicksort. Quicksort is often cited as one of like the killer apps of sorting. So if you wanted to like go out and be like, I'm gonna pick a sorting algorithm, in practice quicksort is generally one of the ones that people point at. Because one, it's simple to implement, but at the same time, it has so many different variants of it that if you wanted to find one that suits your needs, it likely exists. But there's other properties about quicksort that justify this. So just as a quick reminder, so imagine I give you some array. Just I want to remind you of what I mean by a pivot. So imagine I give you some array, and when I do apply quicksort, there's this process called a partition. So it's called partition very often. And your job is you select some pivot. Now, classically, it's very often selected as the first or the last element, but it doesn't have to be. I'm going to mention a couple of alternatives. So if you select, say, the first element, what your job in partition is as the name would suggest, partition the array. So anything that is less than the pivot is on the left side of the pivot, and everything that is larger than the pivot is on the right side of the pivot. So when you're done this partition process, you end up with the pivot will be right here. Everything to the left it will be less than. Everything that's greater it will be on this side. Greater or equal if you have equal or comparable elements that have equal precedence. So if you have this, then what you do is you recursively apply quicksort on the left, and you recursively apply quicksort on the right. But this selection of this pivot is what I'm referring to when I refer to a pivoting strategy. So in quicksort, this pivot, the selection of the pivot makes a very big difference on how it works from an asymptotic standpoint. Has everybody got a quick reminder of what quicksort does? So just remember, it has this partition phase where what it does is it goes through, after picking a pivot, what you do is you then put everything that's less than the pivot on the left side, then you have the pivot, then you have everything that's larger than the pivot on the right side of it. And then you apply quicksort recursively to each side. Are we all good with that? Don't be shy. I'm not going to go into too many details about this because you will have seen quicksort at some point. Anyways, I'm going to just highlight a few things quickly. Okay, so I want to talk about different pivoting strategies just to remind you. So you may have heard of the first or last pivot. So that's the one I just described for you over here. We know that this will take big theta of n squared in the worst case. And it has that average case complexity I mentioned. All of these will have the same average case complexity. I must stress that. So quicksort, in the worst possible way, it's quadratic in the running time, but very often you will run into, it will be hard to run into these instances. The instances that are really bad for first and last pivot, of course, is where if you end up, after you do this partition process, that the pivot sits over here on the leftmost side, and then you end up with nothing on your recursive part on the left first call. Everything on the second call is on the right side. So what happens is you keep partitioning, and you end up having the pivot being the next one on the furthest left. And by doing this, each one of these partition calls takes linear time. And if you have to do this splitting process, how many times? You have to do it up to n minus 1 more times, which means that you're going to have a linear amount of work plus, well, actually, times another linear amount of work, which is quadratic. That's where it comes from. So another one, and oftentimes this was proposed as sort of a remedy for this, is the median of 3. Sometimes there's a variant called median of 5. I've seen medians of 8. There's a lot of different versions of this. So in the median of 3, you select the median. Now remember, median just means the middle position. It's not the average, it is the middle position. Select the median of the first, middle, and last positions to be the pivot. So this is what median of 3 means, is that you'll look at the first, the middle, and the last position in the partition process. So like you'll have your chunk, and then you'll look at the first, last, and the middle, and you pick the median of the 3 of those values. So that'll tell you what position to pick as the pivot. In this case, you still get the big theta of n squared in the worst case. But it gets you one step closer to one of the two kind of the most asymptotically optimal cases you can get with quicksort. The next two I'm going to stress, I am almost certain that you've never seen it before, probably in 210 in its full entirety. If I had another month with this class, I would teach it to you. But this course only has so much time in it. Both of these are rather interesting. They're so-called randomized pivot. So this is often referred to as randomized quicksort when it's being used in this way. So instead of me picking only the first or the last or the median of 3, when I look at my array, I just simply I just flip a bunch of coins, and that helps me determine which position I should select. So I just randomly select one. If you really don't like my intuition of that, you just say pseudo-random if you really need to. So you just have some random number generator that will tell you what position to pick in the pivot. So this is a randomized algorithm. So what I mean by that is that the running time actually depends on what you do with the selection of the pivot. So this is not an average case. This is indeed random. So that means when you give me an input, the running time of this is very simple. It's just going to simply be, okay, it depends on where the pivot is located. Now, the way you determine the running time for quicksort when you have the randomized pivot is you take the expectation of the running time. Now, like I said, if I had another month to talk about this in this class, I would teach it to you because it's rather interesting application of randomization. But I want to make sure you're aware of it, and I want to make sure you know that these randomized approaches do exist. This actually has big theta of n log n. And this is, in fact, going to be worst case expected time. And let's underline the expected part. So when I talk about expected, I mean in technical terms, if you know anything about statistics, I'm saying within high probability, it's going to be that it runs in n log n. So that means that the pivot is going to be like picking a pivot randomly like this will actually surprisingly get you an algorithm that will most likely pick you a nice pivot. So that means in the worst case, you should expect it to run n log n, which does reflect quite nicely with the practical justifications of quicksort. Is that really when you pick a pivot, oftentimes in practice, it works pretty good. You end up with these cases over here that happen where you select the first spot as the pivot. After the partitioning, it's in the first spot. That can happen in the worst case. That's still possible with a randomized pivot. It's just not expected very likely. So by using randomization, we can avoid this nasty case, but it is possible. That's why I write worst case expected time, not that it's actually worst case time. I remember, this algorithm is randomized. That means the running time of it is actually based on some expected value for the running time. So I just want to make sure you know the difference. But I did tell you, and I wanted to bring up quicksort for a reason, is this thing called a median pivot. So in selecting the pivot, when I do this partitioning process, when I did my picture over here, I had it so that the pivot was smack dab in the middle. I would like it to be there, but the way you get it to be there is actually that position has to be the median. So if I end up having it where I'm moving all of them on the left side and then all of them on the right side, the pivot has to be a median of all the values to do that. So there is a way to compute this in linear time. It's called, sometimes people refer to it as the medians sorry, it's median, yeah, median of medians, sorry. Or the fancy name is it's BFPRT. PRT. This is named after all the authors of this algorithm. So if you use this BFPRT algorithm, you can compute the position. It computes the position of the median in big O of n time. Big theta if you really want to go there. So what happens is in quicksort, you have the pivot. I've just added in an extra step for computing the pivot. This takes linear time. The partitioning process takes linear time. When I do the recursive application of quicksort on the left and the right side, that's the rest of the algorithm, right? But I haven't accrued anything from a complexity standpoint asymptotically. It's still linear with each one of my calls before I go to my recursive part. I'll talk more about this, how you analyze recursive algorithms, later in this class. But I just want to give you an intuition with this. So if you're able to do this, you actually end up with big theta of n log n, worst case. And that's not worst case expected. It's worst case, n log n. The reason why I would advise maybe not necessarily using this approach is that the big O notation, or big theta here, actually suppresses a large constant. So remember, like I said, like when you have constants, they get dropped in big O notation or big theta. Well, what happens is this constant ends up being rather large. So in practice, some people will tell you, they advise you against using this approach. Instead, use the randomized approach or say one of these other alternative approaches because they tend to work pretty good already. This just sort of adds some overhead where you have to compute the median. But theoretically speaking, this is an n log n running time in the worst case. So I just want to mention these. I'm not going to expect you to know how you do all of these things in explicit and direct terms. I just want you to be aware of these results. Are we okay with this? Now, how do you know how to implement these? Now, I'm not going to be talking so much about implementation of these sorting algorithms. In 210, I know that you talk about sorting, but I want to focus on more interesting problems, to be honest with you. So these are some examples of where we have upper bounds on given problems. Now I want to talk about lower bounds. So that's going to be this isn't really the focus of this lecture. It's actually lower bounds. So these are all algorithms that people, if somebody were to point them to you and say, hey, here's this problem, they might recommend one of these algorithms to you for those given problems. So I want to switch gears and talk instead about something else. I'm going to reframe this question. Okay, so if I wanted to talk about lower bounds, I'm going to switch around this question a little bit. So instead of me asking questions about there is an algorithm that does this thing and asking about best known algorithms we have, instead I want to say the following. Is there any algorithm that solves blank in little o of some complexity function time? Or you may replace this time with space, for example. That's going to be what we're going to focus on today. So equivalently, if you were saying, okay, well, what does that mean when I want to talk about something? What I'm really saying is what's the minimum amount of time, in terms of time complexity, is necessary to solve the problem? So I would state these type of results in terms of either little o or big omega. Big omega is very nice for representing lower bound results. You're going to see this in a moment. So I'm going to first talk about searching. So I'm going to revisit the search problem. And I want to introduce you to an idea called an adversarial argument. Now, at first it's going to sound highly abstract, but I'm hoping by the end of this that you'll come out of this and say, okay, that makes kind of sense. I'll have to think about it a little bit more, or it may be bing bang on. That's okay. So just as a reminder, so the first lower bound we're going to establish is for the following problem. Given an unsorted array L of n elements, is X in L or not? I just want to know if it's in L or not. So I'm keeping it simple. And the following assumption is the only thing I'm going to assume. Oftentimes when people make presumptions and might want to prove lower bound results, they try to make as few assumptions as possible about the input and what your algorithm is capable of. So in our case, all I'm going to care about is that your algorithm is capable of testing if something's equal or not equal. So unless your algorithm does not do that, this result should apply. So the way I'm going to do this is I'm going to establish a so-called adversary. So I'm just going to give you the general gist of this. So I'm going to introduce the idea of an adversary. This is a common trick, or I'm going to give you the idea for this. I'm going to be very blunt with you. Adversarial arguments, when you get to more technical and much more higher level than this, they get kind of difficult to apply. But at the same time, they do exist and they're very commonly used to establish lower bound results. So we're going to use something called an adversarial argument. To prove a lower bound L of n on solving the search problem, or solving it. I'll keep it simple. Now, I'm going to keep this somewhat informal because you can get very technical with this. So I'm going to introduce you to the idea of an adversary. I'm going to imagine an adversary. If you don't like the word adversary, think of an opponent that you're playing against. So I'm going to be drawing on an analogy of playing a guessing game. And I must stress that this adversary is an intuition. This is imaginary. Like I said, you're imagining it. It's imaginary. And we use this adversary for the argument. Let's use a guessing game. A guessing game to give some background. So I'm going to use a little analogy of a guessing game. And hopefully this will give you the flavor for what I'm going to do. Then when I do the actual example, it should come a little bit more clear. So at first, if you're saying, Dan, this seems a little too high level for me, when I get to the actual example, it should be way more concrete. So I'm going to have more of these details in the notes, so just be aware of that fact. So I want to imagine that you have some algorithm, and it asks questions. Imagine you have an algorithm that asks questions. And these questions, of course, are our guesses about the input. And I must stress, remember, we're not assuming any particular algorithm when we're doing this. I'm just going to imagine you have some algorithm and it makes guesses about the input. So in our case, it would be that we're going to ask questions about the array L. So now I want you to imagine the person that you're asking this from is actually the adversary. And this adversary is going to be malicious. Just malicious. Not going to be very nice. Imagine some malicious adversary that can craft for each guess a worst possible answer. A worst possible answer. A worst possible answer to the question. Now, you might say, Dan, that's kind of strange. What does that even mean? Now, how many of you have ever played the game Battleship? So I'm talking about like literally some sort of board, like it's a physical game. Or you've ever played the game called Mastermind or Codebreaker. In both of these games, they rely on you having some competitor that you play against. So in Battleship, for example, you're playing with somebody else, and your goal is to guess the locations of their ships on a coordinated grid. And what you do is you ask questions like, they kept trying to shoot shots into certain locations on the other person's board. Now just imagine you're playing against somebody in Battleship, for example, that every time you made a guess, the adversary knows exactly what your guesses are going to be, has this all-knowing power to know exactly what process you're going to use the guess to check and see where his or her battleships are. So what the adversary can do is whenever the adversary gives you an answer, you can imagine it like the adversary is cheating, but doing it without breaking any of the rules. So what they do, say for example, imagine this adversary can move around the ships. Whenever somebody makes a guess, imagine they can take a ship that you guessed on and move it over. And say, hey, look, I don't have anything there. You haven't sunk my battleship yet. So they can do that. They're capable of this. They know the process for which you're going to perform the guesses in the Battleship game. If you're thinking about Mastermind or Codebreaker, in that game, what you do is you pause it. The code maker makes a sequence of colored pegs, and they pick them out and they put them behind a protected guard. And the code breaker has to guess the sequence for which these pegs are given in their colors. And you're given a certain number of guesses to do so. So in this case, the adversary has the ability to know the sequence for which you're performing your guesses. And the way you can imagine it from the code breaker's perspective is that the adversary is allowed to meddle around with the combination that the code maker has. Yes, no worries. What I would do is the adversary is able to move and fiddle around with the combination such that it keeps the player going as long as possible. So we're going to assume that this adversary has the ability to know exactly what guesses you're going to make. And remember, because this is an algorithm, it isn't just like an ad hoc process. It's literally that you're given some sequence of operations that occur, and this algorithm is going to perform guesses. In our case, it's going to be that whether it's equal or not equal to an element. So the adversary's job is to craft an instance of the problem. So this is the part that means that it's not really cheating. Is the adversary is going to craft an instance of the problem that causes the algorithm to perform the most number of guesses possible. So the intuition behind the adversary's job is effectively on our reasoning is to craft an instance that will cause any algorithm to perform some maximum number of operations, which yields a lower bound. And our goal is to make this lower bound as big as possible. So the key thing here is that, so I must say it must yield one input or problem instance for your problem. The adversary wants to maximize the number of guesses. Guesses for you to win. So that's going to be generally the idea. We're going to come up with an adversary that's going to craft a problem instance. So that's the big part here, is that this isn't all just poof and magic that the adversary has this power. Is that we're using the adversary to craft a problem instance that, regardless of what the algorithm does, it's going to have to do something to beat the adversary. As in, you have to win the game. But the adversary wants to drag out this process as long as possible. Is the understanding okay with everybody? So the algorithm will perform some guess, and in our case, what guesses will be are going to be checking if something's equal or not equal, or if we're doing a sorting, it's a comparison. And just the goal is that we're going to try to craft an instance that, given any algorithm, under such an assumption, that it's going to take at least a certain number of operations for you to, in our analogy, win the guessing game. Or in our case, for the algorithm to solve the problem. So I put a little bit more detail in the notes if you would like some more intuition. I've also put links to like how you play Battleship and Mastermind if you really just need to see it. If it helps a little bit with what the idea is all about. So I'm going to proceed to my first claim. And once you see this, it should hopefully help you a little bit with everything I've just described for you. We're going to do another example after this, and then I'm probably going to have to talk about it next time, but I'm going to talk about one more lower bound result afterwards. So I'm going to give you the first lower bound I'm going to establish, and I'm going to use an adversarial argument to establish it. So here's a theorem. Given an unsorted array L of n elements, the search problem cannot be solved in little o of n time. Boom. So up to this point, somebody would have told you, oh, linear search, that's like the best you're going to do when it comes to time complexity under no assumptions about the array. Because I'm just assuming it's unsorted. If there was more information I had, this lower bound result may not apply. So the big trick here is that, remember, I don't know what the algorithm is. I do not know that. I cannot make assumptions about what the algorithm's exact process is, just that it performs a series of guesses. In our case, that's going to be checking if whether a spot is equal or not equal to the element. And remember, I'm making the assumption that the algorithm has to be correct. But I could show you another way you can get around this to show that the algorithm can't work, if otherwise. So I'm going to suppose algorithm A. I'm going to give it a name. I'm just going to call it algorithm A. Solves the search problem. So I'm just going to assume it does. The order of the elements examined by A is, I'm going to give them names, I0, I1, all the way up to I n minus 1. Now you might ask, Dan, that seems like an odd, that seems kind of strange. So why are you running it like that? Well, remember, I don't know what algorithm A does. All I know is it examines the elements, right? So I0 could, for example, it's very real that I0 could be position 0. This could be position 1. This could be position n minus 1. I examine these positions. It also could be, I don't know, like 2, 3. It could be it could be position 0 right here at the end. It could be just purely just I try each one, right? It doesn't matter what order it is. That's what this is going to be. So at some point, the algorithm performs examinations. That's all I'm assuming. And this is the order for which it's being done. Is everybody clear on that? So I'm trying to make as few assumptions about what the algorithm does. All I know is it examines elements. So now what I'm going to do is I'm going to construct an adversary. This adversary is going to give me an instance that's going to cause this thing to take as many guesses as possible. And guesses in our case is examining an element in my array L. So I'm going to say construct array L. So I'm going to play on the role of the adversary, but you can always put in parentheses after this construct as an adversary could, array L, so that L sub I0, L sub I1, all the way up to L sub I n minus 2 are all not X. So I'm just going to, so remember, the goal of the adversary is to try to keep this process going as long as possible so that you eventually allow the algorithm to win. In our case, winning means it finds X. So are all not X, and L sub I n minus 1 is equal to X. So the question I have for you is how many examinations have to happen? How many do I have to do for this instance that I just described to you? Notice I've made no assumptions about what order the algorithm does. N, exactly, it's N. Bing, bang, perfect. It's N. So A examines n elements regardless. That says regardless. It's sort of melted there. Therefore, at least big omega of n comparisons or examinations are required. And we're done. Boom. Does this help a little bit with understanding this adversarial argument approach? So remember, the adversary doesn't actually exist. The adversary's job is to construct an input sequence that, regardless of what the algorithm is, it will cause the algorithm to perform the most number of operations, guesses, as possible. So Dan, you might ask, Dan, what if you just didn't assume that the algorithm solves the search problem, just generally? I'm going to give you a quick example. I have enough time to quickly whip out an example and proof, because it's not that long. I'm going to try to quickly whip one together here for computing the maximum. And you're going to see how, even if I make the assumption, so this is involving worst case scenario, but it's very easy to translate a lot of these arguments to other situations. So like this is unconditionally worst case. So But it should look a lot like the worst case scenario to you. I'm glad somebody pointed that out. It's very much intuitively the same idea, except we're codifying the worst case instance in terms of not from our perspective as the analyzers, but from the perspective of any arbitrary algorithm. So notice that's very similar. It has very similar parallels to it. So the big difference here, however, is that we aren't analyzing a given algorithm. We're analyzing any algorithm that does this. So we're looking at it instead from the perspective of any algorithm as opposed to fixing one algorithm and looking for the worst case. So if that helps some people really understand this, that is a very nice way of putting it. But remember, I'm making no assumptions about what the algorithm does. So I'm going to quickly whip together one. So I'm just need a couple minutes here. I just want to give you an intuition with this. Computing. Suppose I consider computing the maximum element. I'll put more of the details in the notes, so I recommend you take a look at that. If I wanted to compute the maximum element, somebody could easily tell me an example of an algorithm that could do that in linear time, right? You would scan all the elements and you would figure out, okay, well, if I find one that's larger, I store that position. I make comparisons as I'm going along scanning from left to right. I do a sequential search. Just like I do with like linear search, instead I always keep track of the largest element by its position. I could do that and I get linear time, right? You might ask, is that the best possible? And the answer is, of course, yes. So I'm going to consider computing the maximum of an array L of n distinct elements. Distinct just means unique. So I can use an argument similar to the one I had before. And no worries, it will be up in the video. I'm just going to whip through this. The way an adversary could frame for this problem is I can think of it like a tournament. So instead of having a tournament, instead of thinking about it just like, oh, I pick positions, I could imagine each element in my array being compared against each other, like a tournament. So imagine you're having some sporting event. So I can compare two elements, x and y. And if I say that x is greater than y, I could say that x wins. And if x is less than y, then x loses. And the element for which it wins always is what we would call, so if it wins always, you could think of it as the champion of the tournament. But this is in fact the maximum, right? This is the maximum. That's the maximum. So I'm just going to write down the theorem here, and I'm just going to give you a gist of the flavor of it, but I'm not going to write it down because I know we're basically at end of time here. And I want to just let you think about it, and you can take a look at the notes if you want to see the proof. So I'm just saying, given an unsorted array L of n elements, any algorithm that computes the maximum of L requires n minus 1 comparisons. Implying that if it's n minus 1 comparisons that are required and your algorithm it means it has to perform this many, regardless. Now, the idea in this proof works as follows. Suppose that you made less than n minus 1 comparisons. So suppose you have some algorithm, it does say n minus 2 comparisons. So suppose it takes n minus 2 comparisons. If you think of like an array that looks like this, It'll compare each element. So it'll compare like the first one, the second one, the third one, the fourth one. If it does n-2 comparisons, there's going to be 2 elements that are still not compared against at some point. And what the adversary will do, because I have not examined these 2 positions, because remember, when I do n-1 comparisons, I know for certain, because remember, I have to compare each element against another element, meaning either x wins or x loses. If I don't do it with n-1, one of them is, of course, x itself, right? So it means I'm going to be exposing one of these openly, right? So what happens is the adversary just simply says, hey, look, you didn't check this right here. I'm going to insert the champion, say, right here. The champion's going to go right there. And boom, your algorithm's wrong. That's all the adversary has to do. So I've written this out a bit more formally in the proof, but you could use the similar kind of rationale with the first proof I did. So if you don't assume that, so if you just want to say, okay, well, I say if the algorithm doesn't perform n comparisons, suppose it's less than n, say n-1, you could just take the adversary and just say, okay, well, I have all those positions that get examined. Well, if you didn't check one extra position, you just insert x or not x somewhere. I'll let you think about it. But essentially, if you preemptively end, in our case, the tournament, or in that case, scanning the array, the adversary can take advantage of that fact and insert something that will cause the array or the algorithm to run longer, or the algorithm will just simply be wrong. Okay, so I'm going to stop right here and say thank you very much and have yourself a beautiful day. So just take a look in the notes if you want to see the proof for this, okay? So next time we'll do one more lower bound example. So I'll see you later.